Hello, everybody. So last time we defined deterministic finite automata, DFA, and we talked about languages that a DFA recognize. And these languages that are recognized by some DFA are called regular languages. And now we want to understand the properties of regular languages. We'll talk about some interesting closure properties of regular languages, and they will turn out to be very interesting in the sense that they are not only properties of regular languages, but they are actually going to define regular languages. So here are the properties we are going to discuss. Assume that you have two languages, A and B. We can define the union of these languages, or strings that are either in A or in B. So just the union of A and B as subsets, right? We said that languages are subsets of words, and we are just talking about the unions. Similarly, the intersection is strings that are both in words that are both in A and in B. The complement of a language is the set complement of the language. All the words such that they are not in A. We can talk about the reverse of a language, which is just the reverse of every word in the language. So W1 up to WK is in the reverse of A if WK to W1 is in A. Concatenation, A concatenated with B, just says that it's a concatenation of words VW, where V is in A and W is in B. And the clean star, so A star is the concatenation of S1 up to Sk, where K is larger or equal to 0, where every Si is in A. So now that we can talk about concatenation of 0 strings, so A star always includes the empty string. The empty string is in A star for every A. Otherwise, it's words that can be split into the concatenation of words from A. And the theorem is that if A and B are regular languages, so are A union B, A intersection B, the negation of A reversed, A concatenated with B, and A star. So this is the theorem, and we'll start working our way through proving it. We won't get all the way, we'll get stuck at some point, but this will help us introduce the notion of non-deterministic finite automata. So let's start with the union theorem for regular languages. Given two languages, L1 and L2, the union of L1 and L2 is just the set union of these two languages, so words that are either in L1 or in L2. And the question is how to prove the union theorem. The theorem is that the union of any two regular languages is also regular. And to prove it, this will denote our proof. We'll recall that L1 and L2 are regular. We need to take advantage of this property. This is essentially the only thing we know about L1 and L2. And the fact that they are regular means that there are finite automata M1 and M2, such that L1 is the language that M1 accepts, recognizes, and L2 is the language that M2 recognizes. And now what do we need to show? We need to show that there is another finite automata M that will recognize the union of L1 and L2. So that's essentially what the theorem says. We didn't do much but parse the meaning of this theorem. So the idea is to construct M that in parallel runs M1 and M2 and accepts if one of them is accepting. So we will run the machine for L1, the machine for L2, and if one of them accepts, so will we. So these are the machines as before. And to run in parallel, in order to run in parallel, we'll define the set of states of M to be pairs of states, where Q1 and Q2, where Q1 is a state in M1 and Q2 is a state in M2. So Q1 belongs to Q1, to the set Q1, and Q2 belongs to the set Q2. So when we're saying that in parallel we're going to run M1 and M2, M1 is going to run on the first component of the state, and M2 is going to be run on the second component of the state. The start state is Q01 and Q02, right? Because we want these to be two parallel runs, and both of them needs to start from the corresponding start states. The accept states are going to be Q1, Q2, where either Q1 is an accept state or Q2 is an accept state. And the transition function is exactly the one that allows us to say that we are running in parallel. So delta that gets the state Q1, Q2, and the symbol sigma will move to the state which its first component is delta 1 of Q1 and sigma, whatever M1 does when it is in Q1 and reads sigma. And the second component is delta 2 of Q2 and sigma. So let's see this transformation on this very, very simple example. So we have M1 and above and M2 below, and now we want to create M. So M will have states that are pairs of states. So Q0, Q1, and P0 and P1. So these are the states: Q0, P0, Q1, P1, Q0, P1, Q1, P1. And these are the transitions. And you can verify that indeed each one of the transitions correspond to running in parallel M1 and M2. So this says that the union of two regular languages is regular. Now we want to somehow argue that the intersection of two regular languages is regular. How will we do that? That's almost the same proof. We just need to change our notion of accepting states. So instead of accepting state being ones where either the first state is accepting in M1 or the second component is accepting in M2, we want both of them to be accepting. So in this example, we need to turn this state and this state to be reject states, whereas the only accept state is Q0 and P1 because Q0 is the accept state in the first automata and P1 is the accept state in the second automata. So this is going to be the only accept state. So in the more formal description, the only difference is that is in the accept states. Instead of asking for Q1 to be in F1 or Q2 is in F2, here we'll ask for Q1 to be in F1 and Q2 in F2. This is, we've proved almost simultaneously. We recycled the proof of the union theorem to be a proof of an intersection theorem. So the union, so it's closed under union and it's closed under intersection. What about the complement theorem for regular languages? So this is the third closure property. The complement of a regular language is also a regular language. So if L is regular, then we want to say that not L is also regular. And how will we do that? Well, we'll take the automata that accepts M, and we're going to revise it to be an automata that accepts not L. What would be that automata? Well, yes, we're going to change every accept state to reject state and reject state to accept state. This kind of shows us that the computation that is always correct is essentially the same as a computation that is always wrong. And we'll discuss it later in the class as well. Right, so that's the proof. The proof is just switching the accept and reject states. So we did 3 out of 6. We should feel very happy with ourselves. And now kind of let's try to do the 4th one. And this 4th one will give us a little bit more trouble. So the 4th one is the reverse theorem. The reverse of the language L is all the words such that when you reverse the word, you get a word that is accepted in L. And the theorem is that if L is regular, then L reverse is also regular. Meaning that if L is recognized by the usual kind of DFA, then L reverse is recognized by a DFA. And essentially, it means that you can recognize L, you can take every right to left computation and replace it by left to right computation. So this is essentially what the reverse means. The reverse means that instead of looking at the string W1 up to WK and asking if it is in L, we're going to read it from the other direction and ask it whether it is in L. So how are we going to reverse DFA? The idea is that as we assume that L is a regular language, let M be the DFA that recognizes L. And we want to build a machine MR that accepts LR. And we're just going to try to reverse M. So if M accepts W, then W is describes a directed path in M from the start state to an accept state. Let's reverse this path and ask for a path from the accept state to the reverse state. So try to define MR as M with the arrows being reversed and turning the start state into final state and final states into the start state. The problem is that this is a great kind of idea, but it doesn't give us a DFA. When we reverse a DFA, we don't get exactly a DFA. MR can have many start states. Some of the states may have more than one outgoing edge, and others will have no outgoing edge. And also we may have more than a single start state. Wait. Let's not be harsh. We don't need to throw out this idea. In fact, this idea will give us something very, very useful. And so let's entertain this idea a little bit further. So recall this is the DFA that recognizes the language that of all the words that contain 001. And let's try to reverse it. We're reversing the edges and we're reversing the start and end state. In this case, There are only one, so one problem is solved here. But now the question is what happens when we compute on the string 1, 0, 0. So we can do various things. We can take 1, 0, 0 and gets to accept. And this is an outcome that we actually want to have because 0, 0, 1 is accepted by the original DFA. But what happens if instead of doing that, we just take 0, stay put, sorry, take 1, stay put, and now when we read 0 and 0, we need to continue staying put. So because this state has two edges marked 1, we can do one of two things. One of them can lead us to accept, but the other one leads us to reject. So we need to define the notion of accepting a little bit different, and we will say that the new machine accepts a string if there is some path that reaches some accept state from some start state. So it's true that some ways of doing the computation, like here, when you start with 1, stay put, and then you stay put with 0 and 0, will actually make you reject. But as long as there is one path that is accepting, then we say that this new machine that is not exactly a DFA accepts. And now we are ready to name this machine. We'll call it non-deterministic finite automata, NFA. And we are ready to analyze it. And so this thing that is a byproduct of trying to prove a particular theorem will turn out to be extremely interesting.